So I'm sure that you noticed in that reactions or the reactions that we've just done is that water has got two options. Water can either have, or water can be an acid and have its conjugate base be OH minus, or water can be a base such that its conjugate acid is H3O plus, because water is amphoprotic or amphoteric. And if water is amphoprotic or amphoteric here, it can do some really interesting things. So note, any solution that we're going to be working with is going to be in water, and water can be an acid or a base. All right, so acid-base properties of water. Water, we know, can act as an acid or a base. So let's pretend here that this water is a base and this water right here is an acid. If this water is a base, it's a proton acceptor, and one of the protons from the water can come over and stick to it. When it does that, it's going to leave us with hydronium and hydroxide. And with one water as an acid and one as a base, it's going to make the conjugate acid and the conjugate base of water. It's going to do this by itself, auto ionization, breaking apart and ionizing such that H2O reacts with H2O to make hydronium and hydroxide. This is at equilibrium, and it's going to occur for all aqueous solutions. So all aqueous solutions, so anything that is in water, is going to have water itself auto-ionizing. Now, why do we care? We care because this is going to generate our pH scale. So if H2O auto-ionizes into H plus and OH minus, now we can write this here as either H2O plus H2O goes into H3O plus OH minus, or we can accept here that we know that H3O plus is an H plus attached to water. So here, these are kind of interchangeable, and they will be used interchangeably. We just need to accept that H plus doesn't exist in water. It really will stick to a water itself, making H3O plus. With this in mind, we can get a K. And we know our K is going to equal our concentration of the hydronium multiplied by the concentration of the hydroxide divided by the concentration of water as a liquid. But remember, we leave pure liquids off of our equilibrium constants. So our equilibrium constant in terms of concentration, which we're going to call Kw, and it is the ion product constant, but we're just going to call it Kw for water, is going to equal H plus and OH minus. So in any aqueous solution, anything that is in water, it will have a Kw equal to the concentration of OH minus multiplied by the concentration of H3O plus. Now the value of Kw is going to depend on temperature. As the temperature goes up, Kw gets smaller, but at room temperature at 25 degrees Celsius, Kw is equal to 1.0 times 10 to the minus 14. So we have terms that we use to describe solutions. If H plus is equal to OH minus, the concentrations are the same, our solution is neutral. If we have more H plus than OH minus, the acid dominates and our solution is acidic. If the OH minus concentration is greater than the H plus, our OH minus dominates and our solution is basic. But the product of H plus multiplied by OH minus is going to be constant in water and will equal 1.0 times 10 to the minus 14 at a temperature of 25 degrees Celsius. And by the way, that is pretty much the only temperature we're going to use. So we don't actually use the concentration of H plus or OH minus. Instead, we use pH. So I need you to think about this. If we have water, so let's imagine that we have H2O, and H2O is going to react with H2O, and it's going to make in solution H3O plus OH minus. Now this is equilibrium, which means that we have an ice chart. Well, if we have an ice chart, these are liquids, and we're going to ignore them. We're going to assume that these guys start out with 0. And if we start out with pure water, these are going to go up by some value x and x, so that at equilibrium, 1.0 times 10 to the minus 14, our ion product, or our Kw, is going to equal x squared. If we take the square root of each side, we're going to find that x is equal to 1.0 times 10 to the minus 7, which tells us that the concentration of our hydronium in pure water, so this is H3O plus concentration in pure water, is equal to 1.0 times 10 to the minus 7. Remembering the units here are molar. Well, we could use these values because that's a tiny number. And instead, what we do is we take the minus base 10 log of it. If we take the minus log of, first of all, the minus log of 1 is 0, so we're going to ignore it. And if we take the minus log of 10 to the minus 7, the log, remember, takes away the 10. And so as soon as the log takes away the 10, it's going to be gone. The negative takes away that negative sign, and so the minus log of 10 to the minus 7 is equal to 7. Now, this is our pH scale. pH, or P, first of all, for a start, by definition, is minus base 10 log. So pH is going to be the minus base 10 log of the H plus. So the H here is referring to the H plus, and P is the mathematical function of minus base 10 log. Well, what does this mean? If we have a pH of 7, it means that the concentration of H plus is equal to OH minus. Why? Because these are both X in our nice neutral solution. And our H plus is 1 times 10 to the minus 7. We take the minus base 10 log of that, we get 7. If we have more H plus than we have OH minus, so let's just imagine that the concentration of H plus is equal to 1 times 10 to the minus 4 molar. So if we look at this, we know that H plus multiplied by OH minus is going to equal 1 times 10 to the minus 14. If we start out with ones here, now note if this value at the beginning is not 1, you have to use your calculator. But if we start out with a 1, we're going to just ignore it and just call this 10 to the minus 4. If we have 10 to the minus 4 for our hydronium, we want to figure out how much hydroxide we have. We know that these are going to multiply together to get 1 times 10 to the minus 14. Well, note we can actually add our exponents to make that work. So if H plus is 1 times 10 to the minus 4, then OH minus is 1 times 10 to the minus 10. And minus 4 plus the minus 10 here is going to give us that minus 14. Note the H plus is greater concentration than the OH minus, which says that our acid dominates and our pH is going to be less than 7. Why? Because the minus base 10 log of 10 to the minus 4 is going to be 4, which is going to be a pH of less than 7. If our OH minus is greater than H plus, our pH here is going to be greater than 7. Note, as the H plus goes down, the pH goes up. So let's play with this one. If we have an HCl solution, so HCl, by the way, is a strong acid. Strong acid, by the way, strong means 100% ionized in water. So it's going to give us a concentration of H plus that is equal to 1.3 molar. If that is the case for our H plus, what is the concentration of OH minus? Well, the concentration of OH minus is going to equal 1 times 10 to the minus 14 divided by the concentration of H plus, which is 1.3, and our concentration of OH minus is going to equal 7.7 times 10 to the minus 15 molar. Please note the concentration of H plus is greater than the concentration of the OH minus. 1.3 is certainly greater than a value of 10 to the minus 15, and this is going to be an acidic solution. Some common pHs. HCl has a 1 molar HCl has a pH of 0. Why would that be 0? Because minus base 10 log of 1 is equal to 0. If instead we had 10 molar, the pH would actually be negative. The pH of 0.1 molar HCl minus base 10 log of 10 to the minus 1. The log again cancels the 10, a minus cancels the minus, and the pH is going to equal 1. Stomach acid is between 1 and 3. Unpolluted rainwater, believe it, is slightly acidic. Your blood is between a pH of 7.3 to 7.4, and we're going to do some math. We're going to realize that 1 molar sodium hydroxide is going to have a pH of 14. These guys are going to be basic, and everything down here is going to be acidic. So if our pH is 1, it's a strong acid. If I got a pH is 7, it's neutral. pH is 14, it's going to be a strong base. And anything in between these guys are going to be weak. Weak as in a weak electrolyte, which means it's going to give us a nice equilibrium, which we love because we can do the math. There are a couple of ways to measure pH. One is a universal indicator, and the indicator changes color with the pH. We can also use pH paper, which is going to change color with the pH as well. We can do those in the lab, or we can actually use a pH meter. In the lab, we're going to use a pH meter. pH meters, in fact, work on the conductivity of the solution and measure how much H plus is in there. We're going to be using these extensively in the lab as we measure the pH of solution. You can actually get quite a bit of accuracy out of these for a good grade 1. A portable one, something with a lower accuracy, might be good to about 0.2 pH units, and they're nice and cheap, but they're nice to have around so you can have an idea of the pH of solutions. All right, we know that the concentration of H plus multiplied by the concentration of OH minus in any solution is going to equal, any aqueous solution is going to equal 1.0 times 10 to the minus 14. So if we look at the concentration of H plus, and it has a value of 1 times 10 to the minus 5, we can do the hydroxide two ways. One, we can do it by inspection, or we can do it on our calculators. We know that the concentration of H plus times OH minus is 1 times 10 to the minus 14. So hydroxide here is going to be 1 times 10 to the minus 14 divided by 1 times 10 to the minus 5, and that's going to equal 1 times 10 to the minus 9 molar. And realize here that if we take and we look at our 10 to the minus 5 from the H plus multiplied by 10 to the minus 9 OH minus, the product of these guys is going to equal 10 to the minus 14. So the same way here, if we're given hydroxide at 1 times 10 to the minus 2, we know the H plus is going to be 1 times 10 to the minus 12. Why? Because the product of these guys is 1 times 10 to the minus 14. We can also tell if these solutions are acidic or basic. The H plus here in the first one is greater than the OH minus, so this solution is acidic. Please note everything is going to have, anything in water is going to have both H plus and OH minus. If the H plus is greater, your solution is acidic, and in this case, the OH minus is greater than the H plus, so this solution is going to be basic. So let's make sure we understand pH and pOH. We know that pH is the minus base 10 log of the H plus concentration, and P itself just means minus base 10 log, so we can also take pOH. Well, pOH is a minus base 10 log of the OH minus. So if we look at this and we want to see that pOH is a minus base 10 log of the OH minus, we can go back and forth between pH and pOH because we know here that the concentration of H plus times OH minus is our ion product value for water, 1 times 10 to the minus 14. If we take a minus base 10 log of this entire equation, we're going to have the minus base 10 log of H plus, which is pH. If we're multiplying these guys together, that's an addition, it's a negative, so it's a minus base 10 log of OH minus, which makes it plus pOH minus base 10 log of 1 times 10 to the minus 14. And again, remember the log cancels the 10 if our value in front here is a 1. And when it does that, we're going to have a value of 14, which tells us that pH plus pOH is equal to 14. So if we want to get pOH, the amount of hydroxide, it's minus base 10 log of the OH minus. We want pH, it's going to be minus base 10 log of the H plus. And note, as our pH gets to be a smaller value, our pOH gets larger. When it's neutral, they're the same and they're both 7. And as our pH goes up, our pOH goes down, such that the sum here is always 14. The sum of the pH and the pOH is always 14. Now, when we have acids, it's easy to calculate pH, but with bases, it's going to be easier to calculate pOH and then realize that pH plus pOH is 14. We're always going to measure the pH in lab, but with bases, we're going to start out and calculate the pOH and then use this equation to find the pH. So let's go back to this one and do some more math. Now we know the hydroxide on this one is 1 times 10 to the minus 9 molar. pH is minus base 10 log of the H plus. So if we take the minus base 10 log of 1 times 10 to the minus 5, we're going to get a pH value here of 5. Our pOH is going to be the minus base 10 log of 1 times 10 to the minus 9. It's going to be the minus base 10 log of this value. And this is going to have a pOH of 9. Please note that pH plus pOH is going to add to 14. And our solution here is going to be acidic. Our pH is less than 5. Now, if we have a hydroxide of 10 to the minus 2, we know that the H plus is 1 times 10 to the minus 12. Our pH is going to be 12, and our pOH is going to be 2. We're going to have more hydroxide than hydronium or H plus, and our solution is going to be basic. Now, we know that pH is the minus base 10 log of H plus. Now, we can work this backwards and get our H plus concentration. So let's make sure this makes sense. If our concentration of hydronium or our concentration of H plus is equal to 1 times 10 to the minus 5, we know our pH is equal to 5. And notice that this 5 is that 5. So to go from pH to hydronium, we're going to take 10 to the minus pH, and that's going to give us the concentration of the acid that is in the solution. Equally, 10 to the minus pOH is going to give us the concentration of hydroxide in the solution. So we can go back and forth between pH, pOH, hydroxide, and hydronium. And we remember that pH plus pOH is 14. All right, so let's continue and do this. If our pH is 6, then our H plus here is 10 to the minus 6. Again, our H plus from our pH is 10 to the minus pH. We know that pH plus pOH has to add up to 14. So 14 minus 6 is a pOH of 8. 8 plus 6 is 14. Our hydroxide concentration is going to equal 10 to the minus pOH, and this is going to be 10 to the minus 8. Our hydronium is greater than a hydroxide, and our solution is going to be acidic. If pOH is 2, then pH is 12, and the concentration here is 10 to the minus 12, and the concentration here is 10 to the minus 2. We have much more hydroxide than we do acid, and our solution is basic. All right, so let's make sure that we understand this. We've got a couple of ways of doing this. And note here, our initial values are not 1 times 10 to the minus something. So we have to do all of these on our calculator. Our H plus multiplied by the OH minus is going to equal 1 times 10 to the minus 14. Our pH plus pOH is going to equal 14. We know that if we have more H plus and we have hydroxide, we're going to have an acidic solution. Vice versa, if it's basic, now here the solution is going to be acidic. So if we want to do this, we can take and get the pH. That's going to be minus base 10 log of 0.015. We plug that into our calculator, we're going to get a pH of 1.82. If we take 14 and we subtract 1.82, we're going to get POH, and that's going to be 12.18. And now we have two options on our hydroxide. We can either take 1 times 10 to the minus 14 and divide it by 0.015, or we can take 10 to the minus 12.18. Because hydroxide is going to equal to 10 to the minus POH, we can do this in either fashion using either equation. And when we do this, we're going to get a hydroxide concentration of 6.7 times 10 to the minus 13 molar. All right, so here, if we have a hydroxide concentration, we can do this again either way. We can take 1 times 10 to the minus 14, divide it by the hydroxide of 6.5 times 10 to the minus 4. When we do that, we're going to get 1.5 times 10 to the minus 11. Our pH is going to be the minus base 10 log of that value. When we plug that into our calculators, we're going to get 10.81. For our POH, we can either take the minus base 10 log of 6.5 times 10 to the minus 4, and when we do that, we're going to get a POH of 3.19, or we can take 14 and subtract 10.81. Any of these work. These equations are going to be very interrelated. We look at this and we realize our hydroxide is going to be greater than our H plus or our hydronium, and our solution is going to be basic. So here we have a pH. We know that our POH is 14 minus that value, and that's going to give us a value of 6.65. Our H plus concentration is going to be 10 to the minus pH, which is 10 to the minus 7.35. Remember, our H plus is equal to 10 to the minus pH. Again, we can go through these in a multiple of different directions, and that's going to give us 4.5 times 10 to the minus 8 molar. Our 1 times 10 to the minus 14 divided by 4.5 times 10 to the minus 8 molar is going to give us a hydroxide concentration of 2.2 times 10 to the minus 7 molar. Our pH is greater than 7, which means our solution is basic. If our POH is 11.45, then our pH is 14 minus that at 2.55. Our hydroxide is going to be 10 to the minus 11.45, and that's going to equal 3.55 times 10 to the minus 12 molar. Our pH is 10 to the minus 2.55, and that's going to give us, and that's pH, excuse me, our H plus is 10 to the minus 2.55, and it's going to be 0.0028 molar.